Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video we will talk about electric potential, which is also known as scalar field, and we denote this scalar field by a letter V. Capital V will use to indicate this scalar field, which is electric potential. Now let's talk about the definition first. So it's a definition which is more popular in books is this. It says electric potential, that is V, at any point is equal to the work done by external agency or external force in bringing a unit positive test charge from infinity to that point. And while we are bringing this charge from infinity to that point, it has to be brought slowly. So these are the crux point that are part of the definition. Let me repeat what I said. It is defined as the potential as defined as at any point. So whatever the point we are interested in, at that point the potential will be equal to the work done by external force when we bring a unit positive test charge Q from infinite location to that location. And while we are bringing that charge, it must be brought slowly. Let's try to use this definition to find out what the formula it is going to be. So let's say there is a particular charge distribution is given. So this is, let's say, any charge distribution which is Q. And we are interested at a point P. At this point P, we want to know what is the potential because of this charge distribution. So in order to find out the potential at this point because of this charge distribution, what we need to do, we need to start with a positive unit test charge running from infinity. So very far apart location, we need to bring or start bringing a unit test charge. So let's say Q charge we are bringing, and that from infinite location. So when we bring this charge from that location slowly and bring this to that point P, during this journey there has to be work done by the external force, the force that is bringing this charge, and that work done will be this potential at this point P if the charge is unit. So let's say during the journey the charge is at this point, let me draw with this black color. The charge is at this point at any instant. When the charge is at this point, so there must be a field because of this charge existing. So let's say that field is existing, so there is going to be a force because of electric field, and to let's say this is acting in this direction. In order to bring this, we need to apply an external force opposite to this, and these two forces will bring this charge from infinity to this P point. Now we know there is a theorem called work energy theorem. So as per work energy theorem, we can write work done by all the forces, that is external, plus work done by electrostatic force must be equal to change in kinetic energy. Now we know as per the definition, we are bringing this charge slowly. The meaning of slowly is that we are moving in such a way that the velocity or the speed of this particle is not changing. That means the change in kinetic energy is zero. Now if this is the case, then we can find out from here the work done by external agency is going to be negative of the work done by the electrostatic force. Now because of this charge distribution which was given to us, we can find out what the electric force is going to be, and if we can find the electric force, then we can also find out what the work done by this force is going to be. Now as far as this electric force is concerned, this force can be written as this force will be Q and E, because Q is the charge that we are moving, E is the field because of this charge distribution, which is capital Q. So this work done, the work done by this force, we need to find and put it a minus sign, so that will become work done by external agency. Now, so as per the definition, potential at point P, if it is V is the potential at point P, definition says it's a work done by external agency per unit charge. So that's divided by Q. Using the above result, we can rewrite this definition as V is equal to negative of the work done by electrostatic force per unit charge. Moreover, as per the definition of work done by a force, we write it as integration electrostatic force dot dr. Now we know the limits from where to where we are moving this. We are moving it from infinite location to the location where the point P is. So up to the point P. And this has to be divided by Q as per the definition, right? Further simplification, this will lead to V is equal to, now let's substitute the value of electric force, which is going to be Q into E. So this will become minus integration Q and the electric field, which we have already calculated or know how to calculate, dot dr, and it's running from infinity to point P, that is point of interest, divided by the charge that we are moving. Now we know this charge Q is this constant number which we can take outside from the integration, and that will be getting cancelled out. So potential at point P is equal to minus integration E dot dr. Now this E is the field because of the charge Q or because of the charge due to which we are interested in the potential, and the limit here is going to be from infinity to the point P. Now we can say this is a result or a formula for us. This formula will be useful to find out the potential at any point because of charge distribution. If we know the charge distribution, we can find out the field because of the charge distribution, and we can perform this dot product and this integration. Then the potential of that point will be known to us. So that's an important result that will be used to find out the potential if the electric field is known to us. Now we can further interpret this result as if the electric field is known to us, we can easily find the electric potential. That means if the vector field is known to us, we can find the scalar field, which further means that the two fields are interrelated. They are not independent of each other, rather they depend on each other. Right. Now we will be using this definition to find out the simplest formula of electric potential, that is because of a point charge Q. So let's see that. So let's take a point charge. So here is a point charge Q located. Let's say this is a point charge Q located, and there is a point P where we are interested to find out the field, and this distance is, let's say, r distance away. There is a point of interest we are interested in to find the potential. Now as per the formula, V is equal to integration from infinite to that location P, which is now indicated by R, E dot dr. We know what is the definition of E and definition of dr in case of point charge. So let's place the formula of field. There was a minus sign, so we need to respect the minus sign as well. It's going to be from infinity to this R location. E can be written as K Q upon R square at any distance R, and R cap dot dr. Dr can always be written as, whenever we require dr as a vector, we can always write this dr vector as a dr magnitude and R cap direction. So this will become dr R cap. Further simplification will lead to minus K Q, which are constants, integration from infinity to the location R, which is the location of point P, and this is becoming 1 upon R square dr and in bracket we can write r cap dot r cap. As per the rules of vectors and the dot product, we know this r cap dot r cap is unity, that is 1. So this integration will lead to minus kq integration. This 1 upon r square can be written as r raised to power minus 2 dr. Limits are from infinity to r location. So this will lead to a potential V as, we know this integration, there's a standard formula, x raised r raised to power n, so n plus 1 power n divided by n plus 1. So it becomes minus kq, and that will be minus 1 upon r, and the limits are running from infinity to small r. So after putting the limits, minus and minus can be adjusted, so this will become kq 1 upon r minus 1 upon infinity. Now we know 1 upon infinity is a 0, so this will lead to V is equal to V, that is potential, is equal to k q upon small r. Now here we have taken this V as a potential, q is the charge, r is the distance from the point charge at which point we are interested in finding the potential, right? So that becomes a formula for us, and we will be using this formula because of point charge. Now here some interpretation points are like field is field depends on this distance as 1 upon r square, and potential depend on a distance as 1 upon r. Now if the charge q is a positive, potential is going to be positive. If charge q is negative, potential will become negative. If charge q is 0, potential will become 0. Potential is a scalar quantity, unlike a field, electric field, which is a vector quantity, right? So this is going to be important, a formula that we'll be using in future. Now here we have taken this point p address as r. If we take this as any other number, so that number, that distance will be appearing in the denominator of this expression at this location, right? So this is important formula to find out the potential because of a point charge at any distance. So we have got two formulas to find out the potential. One that we have listed is this: V is equal to, let me rewrite this, V is equal to negative of integration from infinity to any distance r at which we are interested, E dot dr. So if we know the field, we can find out the potential at any location. Now, and we have just learned, because of point charge, potential is kq upon r. We can also use that point charge formula. So let's say we got a body like this. This is a charge body, which is a charge distribution, which is not in the form of a point charge. And let's say this is the point P, at which point we are interested in finding out the potential. So what we can do, we can say let's take a small element on this body and call that charge to be dq. If this is a charge dq, and let's join this location of this charge with the point P where we are taking interest. So let's say the distance is r. Because of this small element charge dq at a distance r, the potential we can write as a dv, and that dv is going to be equal to k, the charge, which is dq, divided by r. R is the distance. Now if we can find the potential at this point because of a small charge element, we know if we sum up all the charge elements, so we will get all the potential here. So if we are getting all the potential, we need to sum up these potentials, right? So another formula that we are going to have is total potential at any location is going to be integration dv. And if we integrate dv, so we need to place the dv expression, which is here. So it's going to be integration k dq divided by r. We know this k is a constant, so we can further simplify as a v is equal to k integration dq divided by r. So that becomes another important relation in order to find the potential. So we can find the potential using this expression. what we need to find, we need to simply find dq and divide by r, go to the integration. This integration has to be performed over the entire charge distribution. Now in many of the cases we will find that the charge distribution is going to be at a particular distance from the point P. That means if we find r to be a constant, that means it is same for all the point charges, then the formula will become v is equal to integration or rather k. Since r becomes constant, we can take it outside, so k upon r integration dq. If we integrate dq, so that become total charge, hence formula is kq upon r. So this formula will be useful in all those cases in which we will find the charge is located at a particular distance from the given point. So this is just a case in which r becomes constant, so formula is simply kq upon r. We will see several examples of this short, or otherwise we can use this as our result or formula. And this is another way. So we know the two formulas to find out the potential, one using electric field, another using a differential element. Both are important for us. Now here in this first case that we had v is equal to minus integration from infinity to r e dot dr. Here we take infinite as our reference location. Now if we are not taking infinite as our reference location, so this can be rewritten in different format. That means we can write any other reference location. Let's say this is v of 1 point minus v of 2 point. So this is going to be integration from 2 point to 1 point e dot dr. What we have done here, we have taken our reference to any general point 2 instead of having that reference at infinity. So this becomes even more general expression, right? So now let me re-explain what it's trying to say. This is trying to say the potential at point 1 minus potential at point 2 is equal to minus from location 2 to location 1 e dot dr. Now if we place this to location as infinite, this becomes the original case. So that means v2 will behave like v infinite. Here what we used to assume is that the potential at infinite is 0. Now if our reference has non-zero potential, so that has to appear here. So it's a v1 minus v2, that's also called potential difference, is equal to minus from this location, this is a reference location, to location to 1 e dot dr. So we can call this as a one important relation in general, this is to another important relation in general. These two are very important in order to find out the potential or potential difference because of any charge distribution, right? So based on these formulas, we will see several derivations of potentials due to various charge distributions, and that will be in the next video. So please follow them regularly and revise. Thank you for watching. Have a good time.